Welcome back to another episode of Mr. McCune's Minute Science. We are going to tackle covalent bonding part 2 this time. In part 1, we went over the 5 steps to covalent bonding. We kind of left off on step 5. We didn't do much with it. Well, now we are, because we're going to introduce something called double bonds, triple bonds, and a few hard examples of covalent bonding. We're going to take molecules, we're going to add electrons to them, we're going to do an aerial view and a face frontal view to help you guys get there. And I want to say one thing. I did cover double and triple bonds in the part 1 raw footage that I never got to put in the video because it made it too long. I'm going to cut back to that now. Let's look at O2 for example. This will be our first example of something that gets double bonded. So we can't really identify which one will be the central atom because there's only 2 atoms in this entire compound as it is. It's just 2 different oxygens. So I have O and O. Each oxygen is in group 6A, which gives it 6 electrons in its valence shell. Add both of those together. In total, we have 12 valence electrons. We always start with the same process. We're always going to start by giving the 2 atoms a connecting, sharing pair of electrons that brings them together. So I always start with a single bond between the 2 pairing atoms. So now I have a single bond. I still have 10 electrons I got to give out. I know that some of these still need to fulfill their octet. In fact, both of them do. So I'm going to start giving those electrons out. Here's 3 and 4, 5 and 6, 7, 8, 9, 10, 11, 12. Shoot, I've got a little problem. I used all my electrons. I made this oxygen very happy with all 8 of its electrons. But this oxygen here, it only has 1, 2, 3, 4, 5, 6. So the next step is when you do this, when you have this missing electrons, you can't just go find more. We're not going to just make some out of the dust. What we have to do is actually erase a lone pair from one of the already fully set oxygens. So I'm going to erase this lone pair of electrons, which gives me 2 back into the bank. And instead of just putting it here, because that would just give me the same problem, I'm going to make something called a double bond. I'm going to take those 2 electrons, and I'm going to move them in between oxygens, the 2 oxygens. Now, if I look at this, I have 1, 2, 3, 4, 5, 6, 7, 8 electrons that are all being used by this oxygen, right here. All 8 of those electrons are being used by oxygen, fulfilling its octet. And if I look at this oxygen, I can circle all of its electrons, and I can see that it has 1, 2, 3, 4, 5, 6, 7, 8. Now, in order for both the oxygens to fulfill their octet, they had to share 2 pairs of electrons. That created a double bond. So let's get one example of a triple bond up on the board. We have N2. So I have 2 different atoms, 2 nitrogen atoms that are going to bond covalently. Now, nitrogen is in group 5A, which gives it a total amount of valence electrons of 5. There are 2 nitrogens in this molecule, so valence electrons is equal to 10. So I only have 10 to work with. Now I'm going to start doing step 1, the normal step that we always do. Electrons. I've made 1 nitrogen pretty happy, but unfortunately this nitrogen is very sad. So we go back to that strategy of erasing one of the lone pairs. Lone pair meaning a pair of electrons that's not attached to anything else. This one, in between the 2 nitrogen, is not lone because it has a function, it has a job, it's holding these nitrogens together right now. But these ones over here, they're not doing all that much, are they? Right? They're just hanging out doing nothing. So we can erase them and we can move them in between to make a double bond. Now we look back and we see, okay, did we make anything better? I have 1, 2, 3, 4, 5, 6, 7, 8. That nitrogen is great. I got 1, 2, 3, 4, 5, 6. Crap. This nitrogen is not quite at its octet yet. So we need to do one more thing, which is going to erase 1 more lone pair of electrons. Goodbye to that lone pair. And we're going to place that in between the 2 nitrogens to create a triple bond between the 2 nitrogens. Now I have a full octet. If I take my red marker, I have a full octet around this nitrogen, and I have a full octet around the second nitrogen. Both of them are completely fulfilling their valence shell. both of them are perfectly bonded together, but they need to utilize a triple bond or 3 shared pairs of electrons in order to make this molecule happen. So now that we have seen a double bond and a triple bond up on the whiteboard, we want to take those same principles from step 5, we want to apply them to a few of the more difficult problems that we might encounter. The first one we're going to look at is SiS2. Now with SiS2, we need to do the exact same thing as we've done before, the 5 steps. Step 1, determine the number of valence electrons. We'll do that first. So we have 2 different elements in this, or 3 total different atoms. We have 1 Si, and we have 2 sulfurs. 1 silicon, 2 sulfurs. In total is what we're looking for. So silicon is 4 valence electrons. Sulfur is 6. There happens to be 2 sulfurs, each having 6, which gives me a total of 16. So I get 16 total valence electrons for the molecule SiS2. Now, with this, we're going to put this off in the corner over here, and we're going to work on this section. We can take those independently, and I can have Si. Now we have Si out. And I put Si out first because it's going to be our central atom. It's our central atom because there's less of it in the actual molecular formula. We only have 1 silicon where we have 2 sulfurs. So most likely, the sulfurs are going to be the things that bond onto the central atom of silicon. So now I have 2 S's out, I have an Si in the middle, and I got to start bonding these things together. And so when I start bonding them, step 3 tells me to attach each atom with a single bond to start. So I'm going to take some electrons from over here, and I'm going to put a single bond there. I'm going to put a single bond here. And that attached all of my atoms there. So as I keep going through my electrons, I need to get rid of the rest of them. So now step 4 is distribute the remaining electrons. Well, to everything else that needs an octet. 15, and 16. So now I've used all of my electrons. Now we're at step 5. I don't get to create more electrons. I don't get new electrons. I only have the 16 that I was given with SiS2. But what I have to do is I have to take one of these lone pairs that aren't quite doing anything, and I have to remove them. So I gotta find out, okay, I gotta get rid of one of these extra pairs of electrons, and I need to move it between to make a double bond or a triple bond. Now let's look and see why. If I look here, sulfur has 8 valence electrons around it, which makes it very happy. This sulfur here also has 8 valence electrons, but the silicon in the middle only has 1, 2, 3, 4. So it is missing 4 electrons in its octet. Well, we can't just go buy new ones. We can't ionically transfer new ones. So we're going to use what we have. So we're going to take a lone pair that's on the sides, one that's not really doing anything, meaning one that's not actively bonding to something. I can remove it, and I can place it in between the Si and the sulfur, the silicon and the sulfur. Now, if I look at it, sulfur still has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Sulfur's still happy. This sulfur's still happy. Now silicon's getting a little closer. 1, 2, 3, 4, 5, 6. So what can I do? I can take another pair of electrons that I don't necessarily need, it's not actively bonding, and I can place it in between the sulfur and the silicon. Now, all 3 atoms are perfectly achieving their octet by moving these electrons around in this fashion. So that's SiS2. That's how we have to approach step 5. And step 5 is critical thinking. It's problem solving. It's taking the electrons that you already have and manipulating them, moving them around to make it best work for you. Let's clear the board. We're looking at our next covalent molecule, BrC2I. Bromide, carbons, and iodides. So now, we break it down. We have to figure out step 1, the number of valence electrons. We have Br, 2 carbons, 1 iodide, and at the end, a total. Bromine's a halogen, it's going to have 7 electrons. Carbon is 4, and iodine is 7 as well. That gives us a total of 22 valence electrons. Now that we have our 22 valence electrons, we need to start off by identifying the central atom. Well, this gets a little more tricky. Looking at bromine and iodine, they have 7 electrons. The only thing they're ever going to do is make a single bond. They're not going to make double bonds or triple bonds because they only need 1 more electron. So you just start looking at these as terms of what do they actually need. Carbon, on the other hand, only has 4. It's trying to fill 4 spots. And we have 2 carbons trying to fill 4 spots. So instead of having just 1 central atom, we're going to end up having 2 central atoms, both of which being carbon. So I have 2 carbons as my central atoms. And then I have 2 halogens, and we'll do it in order of molecular formula, that are going to be connected here. Step 3, as it always is to place a single bond between each atom. So I grab my handy electrons, and I start making single bonds between all 4 of them. I've used 6 of my 22 electrons. I still have 16 electrons left to distribute, so let's go ahead and do that. There's 6, here's 8, 20, and 22. So what I have done successfully is I've made both of my halogens, bromine and the iodine, full octets. They are good. I look at my carbons, and both carbons only have 6. 1, 2, 3, 4, 5, 6. So we got to figure out some way to get rid of some lone pairs and make some extra bonds. Now, I already said that iodine and bromine, they're not going to make double bonds. So I don't want to take a pair of electrons on iodine over here and move it in between it and carbon, if I could ever pick it up. I don't want it to ever be in this position because they're not going to make a double bond. There's no reason for iodine to ever do that. So instead, we look at these lone pairs on carbon. Well, carbon can definitely make doubles and even triple bonds. So let's start by making one of the carbons very happy. So I take one of the lone pairs and I move it in between. Boom. Now I have bromide happy, carbon completely happy. This carbon, however, is still missing 2 electrons. There happens to be another lone pair over this carbon. Replace it in between both carbons to create a triple bond where the carbons are sharing these 6 electrons and they're sharing their last 2 with their iodine and bromine. So now we've successfully placed all of our electrons, we created a triple bond. There happens to be an easier way to look at all this stuff. And so I want you guys to know in the OneNote section it says a covalent bond can also be represented by blank. And so I want to show you how this exact molecule can be represented without necessarily drawing all the dots. And this might be easier to distribute on Google Docs, because I know we had some complaints with some of it prior. So if I want to take BrC2I, we said that the 2 carbons were central. We had an iodine on this side, and we had a bromine on this side. We began by making the single bond between all of them. We can show shared pairs of electrons as dashes. So a single bond is represented by a single dash. There's my single dash. Now, I still have to remember everything I did with the electrons, and I know that we ended up making a triple bond on carbon. In the show of triple bond, it's just 3 dashes. Now, we still can't forget about the rest of our electrons because it helps us in understanding the molecular shape. So I'm going to go ahead, for the video's purpose, put the remaining electrons on there. Each one of these dashes represents 2 electrons. So I'm going to write something up here in this top right corner, and it's going to be 1 dash is a single bond, 2 is a double, and 3 is a triple bond. So now I have a new way of formatting it, kind of a shorthand version where I don't have to draw as many dots. But I still have to know where those electrons are. But for the sake of our Google Doc, you can use these dashes if you'd like to still do it digitally to make moving around the electrons a little bit easier, because I know that was a difficult part for many of you in that episode. That's it. There are practice problems. Please email me any questions you have with practice problems. Try to rewatch those examples when doing the practice problems if you feel like you are struggling. Try to use really great problem-solving skills. Figure out where the gaps are and use logic to decide that, iodine and bromine are probably not going to have double or triple bonds because they only need one more electron. They're going to do things in the easiest possible way because the universe, no offense, is lazy. That's it for this episode of part 2 covalent bonding. Good luck, ask me questions that you need to, and send me pictures.